Okay, Assalamu alaikum everyone, to the physical and the online participants. Today Dr. Iqbal is traveling, so we will take the class. And what we are going to do is that we will try to practice the right hand thumb rule. As sir has already mentioned that he'll not explain these pulses in future, but he'll just say the name of the pulse that we will use. So you all need to understand that if we are saying we are giving 180 pulse to the magnetization vector, where the magnetization vector will go. Okay, so we will together try to practice this, and I want all of you to participate. And if you don't understand, you can ask as many times as you want. Okay, so this is the first picture. I'll try to show you from here, and then we'll also use the whiteboard. Okay, so as sir has already mentioned that the thumb of our right hand indicates the direction of the radio frequency pulse. Okay, you understand this? Okay, first you can tell me the idea what you have understood from right hand thumb rule, so I can have an idea how much you already have background of this. Can anyone want to explain what right hand thumb rule is? Why we use it? No idea? No one understands it. Okay, that's good. Okay, so we use right hand thumb rule to understand the position of the magnetization vector. And why we need to understand it? Because we need to know, in order to design an experiment, we need to know that where the magnetization vector is. Because your detector, when you are performing an NMR experiment, your detector is in the XY plane. There are three planes, X, Y, Z. You understand this? Okay. So our detector is in the XY plane. So in order to detect the nuclei, that nuclei of interest, we need to bring it into the XY plane. Okay. And sir also gave you an example that, for example, we don't want to see the coupled proton. We just want to see the C13, and we are not interested to see the attached proton. All right. What we can do is that we can bring another radio frequency transmitter, and we can switch on the radio frequency that matches to that of proton. So the protons will be continuously in rotation, and you will not be able to observe them in the NMR spectrum. The other option is that you can, if the magnetization vector is at z-axis plus z or minus z, you will not be able to see that. Why? Because the detector in case of NMR is in the XY plane. So this is the basic idea, and you will understand it in detail when sir will give you an idea about the what is that rotating frame of reference. Because we have not sir has not introduced the rotating frame of reference, so I'll try to explain what I can explain without using rotating frame of reference. Okay. So you can see one example. You all can use your right hand. Okay. Starting from this position, the direction of the arrow is indicating the direction of your magnetization vector. Can anyone tell me that right now at which axis is your magnetization vector? Z axis. Okay. And this is basically your plus Z direction, and opposite to this downward is your minus Z direction. Okay. Now can you tell me that in order to bring this magnetization vector to minus Z, which pulse I can use? 180. Anyone who is confused in this concept can ask it. Okay, because this is a whole circle of 360. Each one of this axis is at an angle of 90 degree from one another. I mean that this Z, the difference between this Z and this minus X is 90 degree. Okay, you understand this? And the difference between this plus Z and minus Z is 180 degree. Okay, so the simplest pulse is 180-degree pulse, which will bring the magnetization vector to minus Z. We will start with understanding when our magnetization vector is at plus Z. I'll not change the direction of or the position of the magnetization vector. So initially we can have an idea to use the pulses and then we can move the magnetization vector. Okay. So for these examples, we are assuming that our magnetization vector is at plus Z. You understand this? Okay. So as you all know that in order to bring it to minus Z, we need to give a pulse of 180. But as I told you that in order to detect the nuclei, we need to bring it into the XY plane, not at the Z axis. Okay. So which pulses we can use? We should at least know that the which pulse will bring the magnetization vector at which position. This is the basic idea or basic aim of this exercise. Okay. So what we do is, this is the picture from Dr. Iqbal's NMR book, which is available in library. You all can go and read this chapter. Okay. So use your right hand. Your right hand is basically, what can I do? I can use the, yeah. Okay, so what we can do is that we can use our right hand thumb and this will show you the direction of the radio frequency. So if I say that I need to give a pulse of 90-degree X, that means the direction is from 90X. Okay, and where is 90X? This position. Okay, this is your X, this is minus X, this is minus Y, and this is Y. You all understand it? Minus X, minus Y, plus Y. Okay. Please respond so I can have an idea that I am able to explain.
90 here, 90. Why? How?
It will go to Y.
I have it. Now it was 90.
Yeah.
Positive 90 for Y. Positive Y.
Yeah.
Or for positive X. How we divide?
Yeah. This is what we will learn during this class. We will start step by step. Okay. So we are going to start from 90X pulse and your magnetization vector is present at plus Z position. Okay. So this is the direction of your radio frequency and this, my fingers are indicating the magnetization vector. Okay. Like this. Can you all do this? Your thumb is indicating the direction of radio frequency. When I'll give a 90-degree pulse, it will bring the magnetization vector at Y. Because the difference between Z and Y is 90 degree. Please remember this is basically a 3D frame. I will not be able to explain 3D because my hand will not rotate in 3D direction. So you also need to imagine this. Okay. So when we are giving a pulse from this side, the magnetization vector will reach at Y. Is it clear? Anyone has objection that why it is coming at Y?
I ask you.
Yeah.
Why not this?
Because this is 3D. In original, when you have a try to imagine a 3D circle. In 3D circle, these are behind you. This minus X and minus Y is behind you. It is not in front. These are in front. Okay? These three are behind. And these three are in front. Okay? So I'll explain you that if I need to bring the magnetization vector to minus X, which pulse I can use. We'll also learn that. But for now, we have started from the first pulse, that is 90-degree X pulse, and your magnetization vector was at Z, so it will bring the magnetization vector to Y. Is there any confusion? You can also draw it. Kindly draw it so you will have an idea. This is the first and the last time that we are discussing right hand thumb rule. After that, you all need to learn it by yourself and then we can help you. Okay. So I like to advise all of you to draw a circle in your notebooks like this. Draw a circle, draw X, Y, Z. Those who don't bring any notebook can take a paper from their friends. Draw a circle and make the magnetization vector at z-axis. You don't need to take picture because this book is available in library. Try to draw it. एक पेज में देखो वो इंटरेस्टेड नहीं है तो ये अभी मैं जब करवाऊंगी तो कुछ समझ नहीं आएगी. Okay, have you all drawn a 3D circle? And your magnetization vector is right now at z-axis. Use your right hand. Use the direction of thumb as radio frequency, the direction of the pulse. This is our magnetization vector. The 90x pulse, which is from this direction, will bring the magnetization vector to y. Okay? Can we move now? Okay, now the magnetization vector is at position y. Okay, here. What will happen if I apply another 90x pulse? Now, the magnetization vector is here and I am applying a pulse from similar direction. Where will it go? Minus z. Are you able to rotate your hand? No one is rotating hand. This is right hand thumb rule. You can use your right hand on the picture that you have drawn. Right now, this is in this direction, clockwise. When you will use minus pulse, then you have to use anti-clockwise, and that you cannot do with your hand. In that case, you have to just imagine. Okay? Yes? Yeah. Right now, if 12 is your z-axis, 12 is your z-axis, and you are giving the pulse from the number 8, let's suppose. Okay? So your magnetization vector is coming between 4 and 5. Or you can say at 4. 4 is your y. Okay? And you again gave a pulse of 90 degree. From 4 it will move to 6. Yeah, the minus 6. Because that is behind the plane. This is a 3D rotation. Okay, your minus 6, minus y and minus z, they are behind you, and plus x and plus y is in front of you.
And also remember that when you are giving the pulses from your positive plane, it will rotate in the positive plane. Okay, you are giving 90x positive pulse from the 90x, it will rotate in the positive phase direction. And when you are giving the minus 90, then it will be behind. Okay, we need to imagine this because she is not having any 3D model right now. Okay.
Okay, your question.
I think it's a little clearer with what she just said. Because now, if this is my x-axis and this is y, the first 90, sorry, and this is z rather. The first 90 takes me to y, and the second 90 is not even possible.
Yeah.
Okay, but that means if I'm going towards the negative x, I'm applying the negative x. Okay, so
yeah,
this is clear now.
Yeah. Okay. Okay. Do you have a video? But I think we first
No, just 5
can
minutes.
you download the video?
No, it takes just 5 minutes.
Yeah, but there will be ads. Download it. Okay, from the girl side, you all have understood this concept? Yes.
For example, minus, if the pulse is from minus 10, then to minus 5 or minus.
Yeah, I'll explain the minus pulses. I want you to understand this step by step. Have you understood that a 90x pulse from the positive direction where your magnetization vector is at plus?
चिकन की मस्ती चटपटा के तेवर शुभ के साथ फ्लेक्स द न्यू NMR NMR spectroscopy has become one of the most frequently used analytical tools to elucidate chemical structure. It is particularly useful for
All the same.
Okay, so meanwhile, Fasi is downloading the video. Is there any other question? We need to download it because otherwise they will be added. It's fine, we'll play the video. Yeah, yeah.
Yes.
Okay, till the video is being downloaded, what we can do is we can use another example. Now place your magnetization vector at Z and give a 90 Y pulse. 90 plus Y pulse and tell me where your magnetization vector will reach. It's present at Z axis and you are applying a pulse from 90 Y direction. Where will it go? Right. Yes, who said minus? And why minus Z? Minus 6, no, not at minus 6. You are applying a 90 plus Y pulse. We already discussed that when we will provide pulses in the positive direction, it will go into the positive plane. It will move in the positive plane. So you are giving a 90 Y pulse minus. Where is minus? The magnetization vector is at plus C. Try to draw it. It's already at plus C. You gave a pulse of 90 plus Y. Y minus 6. Listen, in order to bring the magnetization vector in minus X, now I'm explaining and you are discussing with your friend and then you will give a wrong answer. Okay, listen. When you need to bring your magnetization vector in the minus XY plane, you will give the pulses from minus direction. Okay. The example that I just gave was that your magnetization vector is already at plus C and you are giving a pulse from 90 Y, the plus direction. Where will it go? Yeah, clockwise when you are giving a plus pulse. We are right now in the positive pulses, huh? Okay, he is insisting that we should watch this video. I hope that you can have a better idea and then we will continue the exercise. Okay.
NMR spectroscopy has become one of the most frequently used analytical tools to elucidate chemical structure. It is particularly useful for carbon-based chemical compounds, also known as organic compounds, the molecules that make up all living things, and many substances that we interact with on a daily basis. In this video, we'll take a look at how NMR spectroscopy works and provide a visual metaphor for what is happening at the nuclear level. If we consider a chemical compound, we are particularly interested in what atoms are present and what the arrangement of those atoms are. If we were able to look inside an atom, we'd see a dense and positively charged nucleus. It is the nucleus that NMR spectroscopy detects and gives us a lot of information about the overall structure of the molecule. Here's how it works. Ordinarily, nuclei are oriented randomly, but if we place a sample of a chemical compound in a strong magnetic field at the heart of the NMR instrument, the nuclei line up like a compass needle aligning in a magnetic field and start to precess like a spinning top as it spins on a table. By convention, the magnetic field, designated B0, is oriented along the z-axis. Different nuclei have different spins, and the ones with spin 1/2 can exist in one of two possible spin states. These include the following atomic isotopes.
Okay, he wants.
The hydrogen nucleus, usually.
You don't want to explain?
Ordinarily, nuclei are oriented randomly, but if we place a sample of a chemical compound in a strong magnetic field at the heart of the NMR instrument, the nuclei line up like a compass needle aligning in a magnetic field, and start to precess, like a spinning top as it spins on a table. By convention, the magnetic field, designated B0, is oriented along the z-axis. Different nuclei have different spins, and the ones with spin 1/2 can exist in one of two possible spin states. These include the following atomic isotopes. The hydrogen nucleus, usually referred to as simply the proton, is present in almost all organic compounds and is the one most frequently analyzed by NMR. The precession frequency, or Larmor frequency, is given by the following equation and is dependent on the strength of the magnetic field and the gyromagnetic ratio, which is a constant for a given isotope. If we apply now a short radio frequency pulse, or RF pulse, at right angles to B0, the nuclei will flip down to the XY plane in unison and continue to precess. Let's represent the average magnetic moment of a set of nuclei by this sphere. At equilibrium, the magnetization vector will be aligned along B0 as depicted here. As we've seen, the RF pulse will flip the magnetization vector to the XY plane. The rotating magnetization vector induces a current in a receiver coil. This signal is detected and amplified. We can see that the oscillating signal sweeps out a sine wave with decreasing magnitude as the nucleus realigns with the magnetic field B0. This wave is called the free induction decay, or FID. If each proton sweeps down an FID at the same frequency, then each proton would look identical, and we wouldn't be able to learn anything about the overall structure of the molecule. But here's the key. Each proton is in a unique chemical environment. Let's consider two protons in different parts of the molecule. Each will be exposed to a different magnetic field depending on the electron density distribution. The electron creates its own magnetic field, which opposes the applied magnetic field B0. A proton with a high electron density around it experiences a lower magnetic field and therefore a lower Larmor frequency, and a proton in an electron-poor environment has a higher frequency. Typically, protons in an electron-rich environment are referred to as shielded, and those in an electron-poor environment are referred to as deshielded. Aromatic rings, such as benzene, can induce their own magnetic fields, which can further modify the magnetic field around the proton. Now, if we pulse these with an RF pulse, we will get two signals in our FID, one oscillating at a high frequency and one oscillating at a low frequency. The FID is a representation of the wave in the time domain. The Fourier transformation mathematically converts this to the frequency domain, which allows for a visual representation in an NMR spectrum, with the shielded protons giving peaks at the right side and the deshielded protons giving peaks on the left side. Let's look at an example. Here's a simple molecule with hydrogens in 5 different electronic environments. Each type of proton will experience a slightly different magnetic field strength and will precess at its own frequency, giving 5 overlapping signals in the FID. After Fourier transformation, we will get a spectrum with 5 peaks, each peak representing a proton or set of protons in a particular chemical environment. With this spectrum in hand, we can start to deduce the chemical space around each proton. We have seen that an isolated proton, or group of identical protons, will give an NMR spectrum with a single peak, known as a singlet. Sometimes we will have protons that are close enough that their magnetic spin states interact, what's known as spin-spin coupling. In this case, the peaks do not appear as a singlet, but rather appear as a split peak, known as a doublet. For example, if proton A has a neighbor, proton B, in a different electronic environment, proton A will be affected by its neighbor. Proton B will either be aligned up or down, thus proton A will be a doublet. Likewise, proton B will be split by proton A, and it will be a doublet also. 2 neighboring protons will give a triplet, and 3 neighboring protons will give a quartet. You can even see quintets and septets in some cases. Spin-spin coupling can give us valuable information about the connectivity of the atoms in a molecule because it shows us which protons are close to which other protons. I hope this video has provided some useful
Okay. So this video was very different from what I'm explaining.
First, wait.
Yeah, but it's okay. So now we will come back to our concept that we were using. No, this is a nice video, but it does not relate to the topic that right now we are doing. Okay. Okay, what we can do is we can first understand the individual pulses 90 plus x, 90 plus y, 90 minus x, 90 minus y, and then we will use them together. Okay, so I want all of you to try to use these pulses with me and try to imagine also. Yes?
Please, I don't know if you will get there, but I have a question.
Yeah.
The understanding of what you painted to us if we have our x axis, the x axis, and we apply and we apply the pre-calibrated frequency 90 plus y.
Yeah.
Now, if we have that,
What we have? Sorry.
if we have on minus x.
The magnetization vector is at minus x.
Yes. No.
The pulse is from minus x.
The pulse is from minus
Yeah.
x. Yeah. And we apply the minus 90x. You're on minus x, you're applying minus 90x.
It will not move. If the what I understood, if you can tell me if I understood your question right here or not, you are saying that if the magnetization vector is already at minus x plane, okay, no, where is your magnetization vector? At plus z. Okay, this is what I'm going to explain. I explained you that when your magnetization vector is at plus z axis, what all these individual pulses will do with it. Okay, and you can ask questions after that. I hope this will be clear. My drawing is not very good. Actually, it's very bad. Okay. So I was not able to draw it rightly. Okay. Can you see this circle? To the online participants, you can write your question in the chat box. We are trying to explain it to you as well, but I know that this will be difficult for the online participants. Okay, this is better. Now our magnetization vector is at z direction. Okay, the arrow will indicate the direction of the position of the magnetization vector m0. Okay, we'll start with all the 4 individual pulses because we already know that 180 will bring it to minus z, and if we are giving a 360 pulse, where it will go to the same direction. Okay, so what we need to understand is 90x, 90y, 90 minus x, and 90 minus. Okay, so we have already discussed that 90x plus direction, which will be from this direction. Okay, 90x plus will bring the magnetization vector to this plane. Why not here? Because this is a 3D structure and these are behind the plane. Okay, so we already discussed that it will bring it at the position y. Now your magnetization vector is again at plus z and you are giving a pulse from this direction. I cannot use the right hand, but I can imagine. Okay, from this direction. Okay, like this.
Yes.
Okay, and it will bring to the magnetization vector to plus x, not minus. To bring the magnetization vector at minus xy plane, we will use the minus pulses. Is it clear? So right now, this is a basic concept. If you will remember this, you will be able to bring your magnetization vector rotated rightly. When I say you that I'm using the plus x pulses, forget the minus x and minus y plane. Okay, you don't need to remember that there was any minus x and minus y plane because we are right now in the positive xy plane. Okay, so your magnetization vector is at Z, and you apply a pulse from plus Y, 90 plus Y. The magnetization vector will move here. Why not here? Because this is behind the plane. Is it clear to all of you? Okay. Now we have understood two pulses, 90 plus X and 90 plus Y individually. Now we move to 90 minus X pulse. Okay. The 90 minus X pulse, where it will bring the magnetization vector. Yeah, it will rotate it like this. Like this. So it will bring the magnetization vector at minus Y. Is it clear? And now the final pulse, that is your magnetization vector is at Z, and you are applying a pulse from this direction like this, where it will move minus X. I want all of you to draw all these four individual pulses, so me and Dr. Sumaira can observe individually at your notebooks, because if this concept will clear, you all can move your magnetization vector rightly. Yes.
It means radio frequency sources are from every side.
Yes.
From any direction.
Yes.
Project.
Yes. You can move your magnetization vector accordingly, because when you will visit the NMR lab and you will see the Bruker library, there is a whole range of NMR experiment. What is different in all those experiments? The pulses, the time delays. Yeah. 90 pulse, then 180 pulse. Now you will understand this. The application of this will be clear when the sir will introduce the next topics, that is inversion recovery experiments and all other experiments. But right now, I would suggest that don't go to the application, just understand the concept. So in the next class, when sir will be discussing the next topics and he'll just say 180, 90, so you can have a better idea. Okay? So we are basically preparing you for the next class. Please draw these four conditions. All the students, draw these four conditions on your notebooks. Those who didn't bring notebooks can take a page. Please take a page, take a pen from anyone. And next time, try to bring one pen and one paper with you, because you are coming to attend the class. वन एटी पल्स क्या होता है 180 पल्स तो यूं ले आएगी ना हाफ सर्कल रोटेट करा देगी चाहे बात कर लेंगे अगर आप यहाँ से करवाएं या यहाँ से करवाएं आएगा तो माइनस टी पे ही sorry ask in Urdu so I started in okay can I explain it first पॉजिटिव भी करेंगे पॉजिटिव पल्स की अपनी बात है लेकिन 180 डिग्री आप एक सर्कल को इमेजिन करें और मुझे बताएं कि 180 पल्स किसी भी पॉजिटिव से हो या माइनस से हो कहाँ लाएंगे हाफ सर्कल में अब प्लस की साइड से मूव होकर आए या माइनस की साइड से मूव होकर आए फाइनल पोजीशन तो माइनस डी है कि माइनस डी पे है इसलिए समझ आया half circle is 180 yeah full circle is 360 yeah all these are 90 to one another 90 90 90 90 this is 180 and this is 360 sorry full circle is 360 yeah but that does not have any significance the magnetization vector will be at the same direction so we don't use 360 yeah nuclei at different positions This is not the actual. You are that you are using only one input, that is for now. We are just focusing on program right now. I already told you that you will understand the application once you will take the next step. You want to mimic it? Yeah. 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 It is plus the.
Okay, now. This is the proton under the magnetic field. Shake the pulse. Cross. Cross. 9x. Go back. 91. Hey.
You are not putting it in the proper direction. Where is smiling?
I wish I you get the pulse. The pulse. So you already know we have we have space here.
This is something called that is behind all the up to it not if you you won't understand. That's the imagination. It's up to you. You want to understand it.
This is the thing now. This is the thing. It's a bounce coming from
Okay, students. One of our student will try to explain this in 3D axis, which I am not able to explain. So I want all of you to listen to him and ask questions as many as you.
Let me explain what I have and what I have understood about this theory. Okay. The right hand, if this radio frequency now, okay, if you apply the right hand rule. My line, okay, radio frequency, apply the movement that we share talking about. What is that? How it will be written? Side. Very side. Did agree about the word that thing? This side. With my right. Inside. So that means I have now been with the clockwise. Clockwise or not? Okay. Clockwise. Let's apply. Let's agree about this point first. We have radio frequency about the right hand with the rotation clockwise. Okay. Now this is the nuclear. As you see in the last video, the nuclear randomly move around all the directions. Under the magnetic field, I have said so now magnetic field, how it should be happening in this side. Okay, this side. In making this is let's say this is Z axis. Where is axis X? Okay, this one. What is the one? Hey.
Yes.
This is the positive Y, this is negative Y. This is the positive X, this is the positive, see?
Okay, excuse me. You can stand here because the online participants are not. They want to see you.
We agree. First we say our frequency a pulse rotate like clockwise because you apply right hand. This right hand move clockwise or not? Move clockwise. Okay, now this is we said this is X. What this? X okay plus X plus Y.
No, minus X.
Minus X, sorry.
Plus Y.
Plus Y here. And behind me.
Minus Y.
Okay. This under the magnetic field, we make the magnetic field in the Z direction. Okay. So this proton will take this direction and making this frequency, this pulse coming like this. To where you will be there?
Plus Y.
To plus Y. Okay. If it come here, so where should we? I'm saying clockwise here.
From placement.
Plus
Plus Y. If it come from minus X. Focus on the rotation. Minus Y. If it comes from this side, what is this side? Plus Y.
It comes from plus Y, it will move
Where?
clockwise, will come to plus X.
See the movement is this. Clockwise. Okay. You can see there. You see the clockwise. Okay. If it is this direction, okay. To plus Y. If it come, the pulse come from
Let me help you.
here.
Let me help you.
Yeah.
So you have made from this side that this is XY,
Yeah.
this is X,
Yeah.
just X.
Yeah.
When come the magnetic field from the radio frequency from this side, it will be moved in the clockwise, come to
plus y.
Yeah.
Back again, this is stabilization one. I will come from the radio frequency from plus y. I will apply this from my direction clockwise. It will go to positive x.
Yes.
It comes from the side.
You are explaining the same thing.
Yeah, it's the same. If it comes the direction now, the pulse coming from the minus y. Where will it come?
Why you said direction? You are just taking
Ah,
the Katisana.
because why we say
You are
that?
just
Why we
saying
say
that
okay. It's good question here. He said why this if the pulse coming from this side, why not take this? Yes, this side. Okay, if you meaning that the magnetic field, I will take. I have this. It is like this or not? The magnetic field, it is not like direction. We know. The magnetic field, the shape of magnetic field is like circle. That means any pulse coming, not just hit. No, it make it take with the same direction of the magnetic field coming from the radio frequency. That's mean it like rotation. Okay, I hope this.
We study the effect. And we represent it in the vector form. That's why we just represent in one manner.
I hope it's now clear to all. Okay. Thank you. Okay, now what we can do is we can use. मैं chat box सवाल
Start में act में आए हैं, मैं start में देख लेते हैं ये ज़्यादा कुछ. They are just trying कहाँ जाना.
Another thing I would like to say. Finally.
Yeah, finally.
How we can make direct to what it says. What's the meaning of 90x? 90. Okay, it takes the theta or the angle 90. How the reason frequency makes this 90 theta? According to the time. For example, we see before if the pulse coming from this direction at 90. You say here right there 90. What the meaning of 8? It is right, but how we can do that? According to the reference says about the time. If your pulse take a long time, this it shows a prolonged time of pulse. Not take this stop here because you have long time. The pulse, not just if the pulse is short time, yes, can move it okay. If you make the pulse for a long time, when you can remain, okay. The time will give us the 90 or 180 just to remove the time of the pulse. Thank you.
Thank you. Okay. No, I appreciate that you at least came and you tried to explain. Okay. Okay. So now we will move forward. Okay. So some of you, yeah.
Is the angle proportional to the time?
Yeah.
So if I want to achieve 180 angle,
Yeah.
that means probably I will have less than 12 seconds, 12 minutes.
That you need to determine.
I cannot tell you
We
exactly.
generally do not determine that. For this, there is a different experiment we used to do that.
Sir will explain that
Yeah.
experiment. With reference to time, you will get an idea. Yeah. Okay. No more question? Okay. So some of you were asking that what 45 pulse will do. So if you are giving a 90x pulse and it is going to the direction of y, A 45 pulse will bring it between Z and Y axis. It will be exactly at the half position of Z and Y. Okay, and the 180 will bring it to minus Z. We already know that. Now I'll try to show you an exercise, and I want all of you to do that so I can have an idea. Hmm. पति की शेयर कर दीजिएगा करने दो assignment नहीं सिर्फ Okay, now there are 4 different cases, and based on what we have learned till now, we will try to use that concept and we will bring the magnetization vector accordingly. So your magnetization vector is at plus Z. Okay, you have to answer all of these individually. Always your magnetization vector is at M naught is at plus Z direction for the current situation. Okay, we'll move that also. But for the current situation, let's suppose that your magnetization vector is at plus Z and you initially gave a 90x pulse. Where will it go? Plus Y. Okay. And where a 180x pulse will take it? Minus Z. Okay. And where a 90 minus Y pulse, the magnetization vector is at plus Z and you are giving the pulse from the minus Y direction, from here. Minus X, very good. Okay, now there are 2 pulses, a 90x pulse and a 90x pulse, 90y pulse and then a 90x pulse. So when there are 2 pulses, first use the concept for the first pulse, bring the magnetization vector there and then give the second pulse. So your magnetization vector is at plus C and you gave a 90y pulse initially, where the magnetization vector will reach plus X. Now the magnetization vector is already at plus X and you gave a 90x pulse. If your magnetization vector is at X and you are giving a pulse from X, it will not move. Okay? If your magnetization vector is at the X plane, and you gave a 90x pulse, the magnetization vector will not move. Okay. So I think you all have a clear idea now. If there is any question you can ask. Otherwise, we will share some examples with you. We can email that to you and you can use those examples, try to solve them. And if there is any question, we can discuss in the next class. Yes?
Now, sorry, still on the last question.
Yeah.
If it's on, if we apply the pulse and it's from X and 90Y goes to X plus.
Yeah.
And
First, for the current, if you are talking about the D, I gave a pulse from 90Y, which brings it to plus X. Yeah.
now if we apply another 90Y.
90Y. Okay. Now his question is that you gave a 90Y pulse and the magnetization vector was at. Initially, he's saying that you gave a 90Y pulse. Your magnetization vector is at plus X. Yeah. Okay. And you again gave a 90Y pulse. You gave a 90Y pulse. Where will it go? Minus D. 90 plus 90 is 180. You don't understand what? The first concept or the last? Okay, he said that you gave a 90Y pulse from this direction. Okay, like this. So your magnetization vector reached X. Why -6? I am giving a pulse from plus direction. Yeah, yeah, it is +5. Yeah. I think I'll forget all the concept that I had. I'm sorry, but I'm not able to explain. Okay, I was explaining to you. Your vectorization vector was at +c, and you gave a pulse from 90 y direction. It brings the vectorization vector to 90x. Okay, and now it is already at 90x, and you are giving a pulse from here like this. This is your magnetization vector, and you gave a 90 y pulse. It will bring the magnetization vector to -z. I think this is right. It will not go to -5. To bring it to the -5, you need to give a 90 minus pulse. Yes.
As you have mentioned earlier that if we are providing the RF from the positive plane,
Yeah.
it will rotate the manifestation vector in the positive side.
Yeah.
And if we are providing RF from the negative plane, it will rotate in a negative side.
Yeah.
But if this is true, then why when we are providing a 90x pulse from negative y, it's coming to +x.
We are not giving from -y. Right now we are talking about the plus pulses. Here,
Here is one problem about
which problem?
okay, it's matter.
90 minus y pulse, and your magnetization vector was at +z. It's no, it's coming at -x. The magnetization vector was already at +z, and you gave a 90 minus y pulse. It will bring it to -x.
But as my understanding is coming to +x.
Can you draw that for me? You can draw that on your notebook, and then I can explain. अब आप लोग अपने अपने बैठ के मुझसे चॉइसेस हाँ बताएं जी बताएं कहाँ है
The supply radio frequency from 90 Y and it goes to F and then
90y और वो 90x पर है जी हाँ
and it instantaneously it will come back to that again.
how you want to bring it to plus that again
I am asking this will this be static at this x-axis or
this will be here it will be splitted you will understand it when you will understand an example from an experiment but if you want it to bring back to the z you need to give it a pulse it will not come itself
Or if you are not providing any pulses and you're allowing your nuclei to get relaxed, then ultimately it will come back to your Z.
but that will take time
Yeah, it will take time. But if you are not applying any pulse,
it will be
and you want it back to the Z axis, just allow that nuclei to get relaxed. It will release the energy and it will again come back to its equilibrium position. Okay?
if there is any other question you can ask that Why